Hello everyone and welcome to Astrophysicist Talks About Lasers. This is actually an excerpt from my full gameplay video of Portal Reloaded, where the subject of lasers came up and I decided to talk a bit about how they work in reality and how quantum mechanics gives us problems with them, meaning we can never actually focus a laser to go perfectly straight. So I decided to make this its own video for anybody who didn't watch that. If you did, there's nothing new here. Feel free to skip this one. But if you did, I hope you enjoy the discussion. Alright, so earlier in this episode, I talked about the uncertainty principle. So let me explain to you what exactly that is. So let's say we have a particle, and we want to describe where the particle is and what it's doing. Now let's say this particle exists in a one-dimensional universe for simplicity's sake. There are, in that case, two properties of note to describe momentarily what the particle is doing. There is its position, which we'll call x, and its velocity, which we'll call v. Now, from a quantum mechanics perspective, what we actually care about is its momentum rather than its velocity. So we will say its momentum, which we calculate by multiplying it by its mass, and we'll call that the letter p. So for any given particle, we have two properties we care about: its position and its momentum. And if you want to get its speed from the momentum, you just divide it by the mass. So what is the uncertainty principle? Well, the uncertainty principle basically says that there's a fundamental limit to how accurately you can know both the position and the momentum of the particle. So putting it in scientific terms, which don't worry, I'll explain this later, the uncertainty principle says sigma x times sigma p, here we're using implicit multiplication here, just putting one variable beside the other, is greater than or equal to the value h bar over 2. Okay, so let's explain this equation here. Let's start with the right side, as this is the easy part. H bar is called the reduced Planck's constant. If you've heard of Planck's constant, H bar is equal to Planck's constant, the letter h, divided by 2 pi. Really, all that you need to know on the right side is that this is a constant value, that nothing in the system affects it, nothing we do in the universe affects it. This value is just hard-coded into the source code of the universe. Also of note, this is extremely small, so it doesn't come up in day-to-day activities, but it is non-zero. Okay, so what about the left side? What does the sigma mean? Well, the sigma is, roughly speaking, the uncertainty in something, or the statistical deviance of it, if you want to get a little bit more technical. So sigma is used traditionally to mean the standard deviation of something. So for now, let's just say that's uncertainty, then I'll go a bit more into the details later. Okay, so what this equation is telling us is that the uncertainty in the position multiplied by the uncertainty in the momentum of any given particle is always, at all points in time, all points in space, whenever we look at it, whenever we do anything to it, always going to be greater than or equal to this constant small value. So what does this mean practically? Well, practically it means that if you want to reduce one of these, you can only do so to a certain extent before you have to increase the other. So let's clear the screen and let's just talk about uncertainty and what it actually means. Okay, so let's just give a brief overview what the uncertainty of x is. If you've done statistics, you know what standard deviation is, you can skip over this. So let's say we have a particle, we don't know where it is, but we know it is probably close to 0.0. And we've got a number line of all the points it could be at. It's probably close to here. It might be a bit to the right, it might be a bit to the left. On average, it's going to be above 0. If we were to look at this, reset the universe to re-randomize things, look at it a million times, add up all the positions, average them, the average will be close to 0. But any given time we look at it, it might be a bit to the side. We might find it off to the right, we might find it to the left, we might find it way to the right, way to the left, close, could be straight in, a bit off. There's a whole lot of points it could be at. And so what the uncertainty is it's basically giving you a typical distance that the particle will be found from its average point. So if you have a cloud that looks something like this, you can think of the standard deviation as being, okay, what's the average distance away? Now, properly speaking, it isn't quite the average distance away. It is, if you really want to get mathematical about it, it is the square root of the average of the square distance away. So, actually, no, that's wrong notation. That's the absolute value. So what this notation is saying is basically you take all the distances away for all of the trials. For each of them, you square them. Then you take the average of all those squares, and then you take the square root of that average to get the typical distance away. That's how this is defined. But all you really need to know is sigma x is the typical distance away from its average position. And similarly, sigma p will be the same except for momentum. Okay, so let's remind you the equation we're working with. We have uncertainty in x times uncertainty in momentum, which directly translate into uncertainty in velocity, is at minimum this small constant value of the reduced Planck's constant, which if we're just speaking casually and quickly, we call h bar because it's the letter h with a bar through it, divided by 2. So this has been calculated through quantum mechanics. I'm not going to go into proving it here. I'm just going to tell you what it means. So what does this mean? Well, practically speaking, it means that there is a limit to how accurately we can simultaneously know both the position and the momentum of something. So let's say you want to reduce the uncertainty in the position as much as possible. So let's say you want sigma x to be a very small value, let's say 1 times 10 to the ridiculously small 10 to the negative 99. So basically this is scientific notation for writing a 0.89 zeros and then a 1 meters. So we want our sigma x to be ridiculously, obscenely small, even by quantum mechanics standards. It is as small as we can imagine. Okay? Well then, what does this equation at the top tell us? Well, we can just rearrange the parts of this equation to tell us something about the uncertainty in the momentum. So that means sigma p is going to be greater than or equal to, we just divide each side by sigma x. So sigma x times 2 or we can put in the values. H bar divided by, 2 times 10 to the minus 99. Oh, but you might know that if you have a negative exponent in the bottom of a fraction, you can make that a positive exponent in the top. So you could have h bar times 10 to the positive 99 up here divided by 2 meters. So when we want this ridiculously small uncertainty on position, that's going to turn out to, we've got a pretty big uncertainty on momentum. But now we're in the regime where it actually matters how small h bar is. So we're going to need to get some actual numbers for that. So the actual value for h bar is, roughly speaking, 1 times 10 to the minus 34. I told you it was ridiculously small. And the unit, it's typically given in our joule seconds, which a joule second isn't actually the most useful for us. Probably the most useful way to write the unit would be kilogram times meters squared divided by a second. Yeah, this is a constant that we're using for our calculations, and it goes into a lot of things. So the units of the constant itself don't always make direct physical sense, but what comes out of the equations will make sense. So let's put this back into our equation here, and we'll get that value. So our greater than or equal here, sigma p is greater than or equal to. So on the top, we're going to have 1 times 10 to the minus 34 times 10 to the 99. So when you're multiplying things with different exponents together, you add up the exponents. So we add 99 and minus 34, or 99 minus 34 is 65. So we get approximately 10 to the 65. And then we'll have our units here, kilogram meters squared per second. And on the bottom, we have 2 meters. So we can cancel out the units a bit. We'll cancel off the square on the meters and the 2 there. So our simplified equation, putting everything together, is that the fundamental limit for uncertainty in momentum is 0.5 times 10 to the 65 kilogram meters per second. So let's put that into context for how big this is. This is already, we've got a huge exponent here. So this means, like, okay, well, first of all, how much does our particle weigh? Let's say our particle weighs 1 kilogram to keep things simple. That means our uncertainty in its speed is 10 to the 65 meters per second. For comparison, the speed of light is about 3 times 10 to the 8th meters per second. So this is 57 orders of magnitude greater than the speed of light, which is to say that the momentum of it could plausibly be anything in the universe. It's not actually going to be greater than the speed of light. That's about the only limitation. But relationship between speed and momentum actually changes a bit as you approach the speed of light. So basically what I'm saying is, you try to narrow down the position of this particle to this much, its momentum is going to be whatever the hell it wants to be. It wants to be going basically the speed of light. It's going to be going basically the speed of light. So what does this mean, and what does it have to do with lasers, which is the context I actually brought this up in the first place. So we'll clear ourselves off and just start with this equation again. So what is a laser? a laser is basically saying that we want to have waves of light coming out of a thin opening. So basically, imagine this is all filled with light, and light will be in there bouncing around. We want to do something to it so that all of the light coming out will only come out through a thin opening here. So like put a little end here, but still light might be coming out of it at multiple different angles. So let's say it's reflective in here to keep the light contained but without losing it. But we want it to escape through a thin opening. So we'll create a very thin, very long opening. This is kind of a simple way to create a laser. It's not how actual ones work, but we don't want it to bounce through sideways. So here, instead of this part being reflective, we'll make it absorptive, so that you can imagine, light can bounce around in there, but any light that goes through this opening, if it ever hits the wall, it gets absorbed by the wall. So the only light that can get through the opening is light that's going basically straight through. So the result of that is that light that comes out will be going basically straight. But with this type of opening, there's already a bit of a limit that you don't want, that you could have it going from an angle like a bit down to a bit up. I'm exaggerating here, but it could come up like that. It'll still be focused more than you initially had, but it will spread out a bit. But that isn't actually what limits how tight a laser can be. So let's zoom in on our opening a bit. So this is just zooming in on this part. And let's think about the light as it goes through here. So as the light is coming out, what's actually going on is that we've limited its position. We've said that the position of the light, at least in the y dimension, is limited to being in here. So basically, the size of this is going to be, broadly speaking, some multiple of sigma x. So let's say, actually, let's not put that 2 in there. Let's just use rough approximations. Let's say that this distance is going to be approximately sigma x. So some small multiple of it. We don't need to worry about the specifics to highlight things here. So when we have a laser that works like this, we're compressing the exit pupil of the laser to some diameter, and then the sigma x of the light, at least perpendicular to this, is going to be proportional to that diameter. So as soon as we do this, this is going to have an effect on the momentum of light in this dimension. So this means that we can go back to our equation up here and say that uncertainty in the momentum is greater than or equal to h bar over d. We're ignoring these rough constants right now. So what this means is that vertical momentum of the light, now light is weightless, it does have momentum, but you need to use a bit of relativity to calculate what it is. This means that the vertical momentum of the light, that is how far the light is traveling up or down, is going to be, at minimum, this small value of h bar over d. But the smaller you make d, the bigger this uncertainty is. So there are a couple things you can do. You can have a big exit pupil for the laser and low momentum uncertainty, or you can have a small exit pupil and big momentum uncertainty. Either way, you aren't going to be able to make the laser infinitely thin. Okay, let's take this back to our laser example. We've got a small distance, d there. Let's say very small, 10 to the minus 10 meters. Then we plug it into our equations. We get uncertainty in momentum is greater than or equal to h bar over 2. We're skipping the 2 there. times 10 to the minus 10. That gets flipped over. We put it back up on the top. H bar times 10 to the 10 meters. So what does this mean practically speaking? Well, we want to relate it to what the light is actually doing, and there are a few useful equations we can use. One of the most is that the momentum of light is equal to Planck's constant, not reduced, divided by its wavelength. And let's say we just have a ray of blue light. A typical value for light that might be visible could be around a few hundred nanometers. So let's say the ray of light is 600 nanometers, which is equal to 6 times 10 to the minus 7 meters. And again, we're just going to round to the nearest order of magnitude. I'm just making a point here. So 6 closer to 10 than to 1. So we'll say this is approximately 10 to the minus 6 meters. Okay? So putting this up here, bring that on the top, we have h times 10 to the 6 meters. Okay, so what about the uncertainty here? So let's look at these two values. So h bar is close to h. It's like roughly 1 order of magnitude less. So if we want to just correct these so that they're both in the same unit, we could change this to h bar there and add an order of magnitude here. So this is about h bar times 10 to the 7 meters. Don't worry too much about the specific values. We're just illustrating things here. So for a ray of blue light, its momentum, going straight out of the aperture is about 10 to the 7 meters, but the uncertainty in its momentum is 10 to the 10 meters. So this means our uncertainty in its momentum is 1,000 times as large as the overall momentum it has. So if we try to squeeze the pupil this small, then yeah, we can get it to exit a small level, but quantum mechanics says that even if we think it should be coming straight out, no, the uncertainty principle rules the day, and the uncertainty principle says that when you have something coming out of an aperture like this, whatever you think it was doing coming through, the second it goes through this, the uncertainty principle comes on and it can shoot out in any direction it wants. And what actually ends up happening is the smaller the aperture you have, the greater the spread. So that is to say, if you have a wide aperture, you'll spread out a bit. You have a smaller aperture, you'll spread out a lot. And you have to have a teeny tiny aperture, you'll spread out a ridiculous amount. So when we try to make our subatomic aperture, we get the light going basically anywhere. It essentially comes out of the aperture in a flat sheet, doing whatever the hell it wants. So this gives us a problem if we're making a laser, that none of these options have a thin focused ray of light. With a wide aperture, it spreads out a little, but it started pretty thick. With a small aperture, it starts thin, but then spreads out a lot. So if you want a laser that, like, let's say you were looking 1 meter away. So let's say we have a 1 meter distance out here. Then we're looking at the spread. There's going to be some fundamental limit that there is no way to get the laser to focus tighter than that fundamental limit. Then it actually turns out this depends a bit on the wavelength of light, what that limit is, and I'm not going to go over the calculations because it doesn't really matter what the specific limit is. But this is the problem we have with lasers, that there is, physically speaking, no way to get a laser to perfectly focus. And so... Thank you very much for watching, everyone. If you enjoyed this video, please leave a like, subscribe, and click the bell to be sure you get notifications of new uploads. See you again soon.